So we have two threads, T1 and T2. They need to perform some operation involving some variables A and B. And in fact, the two threads don't even need to perform the same operation on A and B, but let's say they both need to access these shared variables A and B. Before performing these operations, they must log the mutexes that protect the shared variables A and B. And let's say T1 first logs the mutex for A, and then logs the mutex for B. And in the case of T2, T2 first logs the mutex for B and then logs the mutex for A. And this is where the problem is. The two threads are waiting on each other in a cycle. Neither one of them will be able to get to the foo operation. Neither one of them, in fact, will be able to execute the second lock operation. They'll keep waiting on each other and we'll have a deadlock. So how can we avoid these situations? One way to avoid this situation would be to unlock the mutex for A before locking the mutex for B, or the other way around. We would call this fine-grained locking. The problem with this is that it won't work in this case since the threads need both A and B, so they have to have both locks. They need both variables after all. Another possibility would be to get all the locks up front and then release them at the very end. Or maybe we just end up using one mega lock, some mutex m sub AB. This solution may work for some applications. However, in other cases, it can be very restrictive because it limits the level of parallelism that can exist in the system. And the last and the really most accepted solution is to maintain a lock order. If we force everyone to first get the mutex for A and then the lock for B, the problem will not occur. If we investigate this a little bit more, we see that the problem is that T1 is waiting on something that T2 has, and T2 is waiting on something that T1 has. So we have a cycle, basically. And in this case, we have two threads, so it's easy to reason about the situation and to determine that the order in which these locks are being acquired can result potentially in a cycle. In principle, this type of analysis is a little bit more difficult to illustrate and to determine, but what we're trying to really show is that if there is a cycle in this kind of weight graph in which we draw a line between two threads, if one thread is waiting on a resource that the other thread has, then a cycle indicates a deadlock. Maintaining a lock order will prevent such cycles from occurring. So we'll ensure that there will be no deadlocks in the code. So to enforce this kind of maintain lock order principle in the example before, T2 would have to get the mutexes, the mutex for A first and then the mutex for B. And there's no way then in this code a cycle would occur. There's no way that a deadlock can happen. So consider this. If thread 1 is waiting on the lock, is about to execute the operation lock M of B, it means it already has acquired the mutex M of A. If thread 1 already has this mutex, then thread 2 cannot have it. So thread 2 must be somewhere before this lock operation in its execution. That also means that thread 2 could not have acquired the M underscore B mutex. It doesn't have it, and therefore there's no cycle. Thread 1 is not going to end up in a situation in which it has to wait on thread 2 for that particular lock, so it will be able to acquire it and continue. So this type of technique will always work. The only potential challenge is that in complex programs that use many shared variables and potentially many synchronization variables, so lots of mutexes, take some effort to make sure that these are indeed ordered and everywhere used in the same order. But as a technique, this is foolproof and it guarantees that it will prevent deadlocks from happening.